So we have another situation. The situation is there are 4 bunnies in a pen. Every month, the number of bunnies double. So if you ever have had bunnies, they have babies really fast. So this situation actually isn't that uncommon. But it's going to be the same instance for our algebraic expression. We want to describe this situation using a table, graph, and an equation. So just like in linear functions, we want to determine what the start is and what the change is. So where are we starting? How's the situation changing? So first, let's do the start. The start, how many bunnies are we starting with? Well, there are 4 bunnies in the pen. I'm going to underline that in blue. And we're starting with 4 bunnies. And I'm going to write down here, the start is 4 bunnies. Now, what is the change in my situation? Well, every month, the number of bunnies double in population. Double is the key word. Double means it's multiplying by 2. So the change is times 2. Now this is different from linear functions. Linear functions is when the change is a constant addition or constant subtraction. Here, it is a multiplication. So when we're constantly multiplying or constantly dividing, we won't call that a linear function anymore. Instead, we're going to be calling that an exponential function. We're still going to be describing this using a table, graph, and an equation, which I'm going to do right here. All right. So we want to make an XY table. I'm going to start with a table that's easiest for me, at least for me, for going from situation. I like doing the table first. You could do it whichever order you want. Doesn't really matter. The table is going to be, we're comparing the x to the y, the dependent variable and the independent variable. Or I say the independent variable is the x. So the x, how much time is passing every month. The x is going to be the month. And the number of bunnies is dependent on the month. So that's going to be my y value, the number of bunnies is my y. Okay, and the months we're starting with 0, 1, 2, 3, etc., etc., etc. Okay, so the start. How many bunnies are we starting with? In month 0, how many bunnies are we starting with? We look at our situation, 4 bunnies. We also wrote down here, we're starting with 4 bunnies. So in month 0, there are 4 bunnies. And every single time, every month that passes, we're doubling the population. So we're multiplying it by 2. So the next month, we're doing 4 times 2, which is 8. And then we're doing it again. To go from 8 to month 2, we got to multiply this population by 2. 8 times 2 is 16. Again, to get to month 3 times 2, 16 times 2 is 32. So every month, the change is doubling. And in an exponential function, the more time passes, the amount gets more and more bigger. It gets so dramatically bigger as more time passes, which is actually very relevant in this time with the coronavirus and everything, how the coronavirus spreads exponentially. We're also going to, so back to the bunnies, we're going to label the start and the change. Here, the start, which I already wrote in blue, is 4. We're starting with 4 bunnies. And the change that we wrote down here, and also we extracted from the situation, is the doubling, the times 2. So to go from 4 to 8, I'm multiplying that by 2. 8 to 16, multiply by 2. 16 to 32, multiply by 2. I'm multiplying 2 every single step of the way. And because we're talking about an algebraic function, we're going to say that this change is going to last forever. all the way into infinity. Obviously, that's not true in real life, but in algebra, we're going to say it's true all the way into infinity. Okay, next up is the graph. Again, you could do equation or graph, doesn't matter the order, but I'm going to do the graph. Okay, and now I'm going to label my my points. 1, 2, 3, and the y, it's kind of a lot. It's going up to 32, so I want to space this out, let's say by 5s. So we're going to do 5, 10, 15, 20, oof, I'm going to 25, 30. Okay, we're going to plot the table onto the graph using the ordered pairs. The first ordered pair is 0, 4. When x equals 0, y equals 4. So it looks somewhere around here. Next up, when x equals 1, y equals 8. That's my next ordered pair. 1, 8, so x equals 1. And I go all the way up to 8. Next is 2, 16. So I go x equals 2, and I go all the way up to 16. X is 3, y is 32, so 3 all the way up here, 32. So one thing that we're missing in the table that I actually forgot to put in, what happens when x is negative? Are we going to go underneath this x line or x-axis? Well, remember that for exponential growth, we're multiplying by 2 every single time. So to go backwards, we're going to divide 2. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. For negative 1, 4 divided by 2 is 2. 2, and the next one, 2 divided by 2 is 1. We're getting smaller and smaller and smaller, but we're never going to be crossing the x-axis. We're always going to be hovering above the x-axis, which is very unique. Well, I don't know about unique, but it's very special for exponential functions. This is my graph. Remember, we're not crossing the x-axis, and it's shooting up. It is not like a straight line, like a linear function. The linear function, which is pretty much what's being done in Algebra 1, deals a lot with lines. This graph is not, we're no longer in Algebra 1. This graph is curved, and it's because the change is multiplying. And speaking of the change, I'm going to identify that on the graph. Every single time I'm doing times 2. This is times 2. Again, I'm doing times 2. And notice that the errors are getting bigger and bigger and bigger. That makes sense because if you're doubling something that's huge, it's going to get even bigger. If you're doubling something that's tiny, it still grows, but in a smaller degree. Okay. Last but not least, we're going to do the equation. And in your Algebra 2 class, hopefully you derive the equation. And if you don't remember, here's what it is. Y equals b times m to the x. And in some textbooks, it's a times b to the x. I'm keeping b and m because in Algebra 1, b is the start and m is the change. I'm going to do the same thing here. So we're going to plug in our start and our change. The start is 4 in the graph, in the table, in the situation. I'm going to plug that in my b value. Y equals 4 times m, or the change to the x. The change is 2. We see that in the graph. We see that in the table. We see that annotated here. We see that in the situation. 4 times 2 to the power of x. And then we're done. The reason why we have this equation like this is because this exponent is telling us how many times we're multiplying 2. When we're at x equals 3, we've multiplied 2 3 times. Therefore, we're doing 2 to the third. But yeah, so we have the equation. I'm going to underline that, or I'm going to box it. The equation, the graph, the table, and the situation, all describing this bunny population.